Hey everyone, how's it going? Welcome to the stream. So I was unable to stream last week. I was actually sick most of the week, and yeah, just not able to actually do this. I'm actually still not 100%, but definitely well enough to stream, so that's really good. So, and since last stream, I haven't really looked at all at any of this stuff. I had started working on sound and had started implementing some stuff, but then actually I kind of got, while I was sick, took the opportunity to start reading more about Rust. I've been meaning to get into Rust for a while now, and so it seemed like a good opportunity since all I could do was sit down or lay down. And yeah, really amazing stuff. Really enjoy what I'm learning about Rust so far. Coming from my extensive C++ background, I'm finding Rust to be a very unique and interesting language. I love how they're solving the whole memory safety. Sorry, my chair is a bit weird. The whole memory safety issue in a completely different way from what I've seen in most languages. So if you're looking for an interesting systems programming language that doesn't have the sharp edges of C++, I definitely recommend taking a look at Rust. At some point, I will probably start a project in Rust, and I will start a project in Rust, but I will probably stream it. So anyway, I'll let you know when that happens. But yeah, let's get back to the program. So what I did do last time, if we go back, we started implementing stuff. We added this SDL audio driver, which I took from my NES emulator. And what we did last time, and I think I worked a little bit on it after the stream, it was putting into place this PSG class. Let me actually go in the code. I think it's going to be a bit easier to see it here. Yeah, so this is the beginning of an implementation of the AY38912, which is a programmable sound generator, this PSG chip. And I don't know 100% about whether I'm going to keep it the way it is, but this music is a bit nuts. Anyway. But yeah, basically there's like this kind of a state machine that I had to implement. I think on stream it was a little bit different. Off stream I thought a bit more about it and I implemented it a bit more straightforward as a state machine here. So we have this enumerator. Basically this chip kind of goes into 4 main states. And these states are driven by certain inputs, this BDIR and this BC1 input. And basically when you switch these on or off, it puts us through 4 different states. 2 inputs, 4 states. And it basically is between inactive, read, write, and this latch address state. So I tried to model that here by having this little function that just checks what were the values we stored. Let me see here. So yeah, we store these bools for BDIR and BC1. I figure out what the mask is. I set a mask based on those values, and then we switch on that mask value and get either 0, 1, 2, or 3. And then based on that, I check. There's a couple of things we want to check in there, like if we entered the read and we were in inactive, at that moment we actually want to read from the currently latched address. Similarly for write, if we came from inactive, because you always have to go back to inactive and then towards these states. So you can see that here. You have this inactive state that does nothing, but read, write, and latch address all do something if we came from the inactive state. And they do this thing once. So that's basically it. That's all I have so far. And this was based off... Can I actually find where I was reading this? I think it was in here. This is the problem with... waiting 2 weeks before before working again on this, because I don't really remember But yeah, I wasn't here. I can see Bidder. And then there was like a, yeah, I remember there was like some kind of state machine. Here it is. So here we can see inactive, output address. What you're supposed to do is go to inactive, then output address, inactive, output data, inactive. So that's a latched on an address that we set. Go to inactive, and then this would be like a read data, and then go back to inactive. And then here similarly, this is for writing data, address, and write data to PSG. Oh, okay, so we output an address, then we go back to inactive, and we output data to it. And then similarly for reading, it's inactive, output, inactive, input, inactive. And then there's some stuff here about bus control. I don't know if I really have to handle any of this. We'll see. I mean, we're just emulating this, right? So I just mainly need to get these values in. And then I think, well, we'll play it bit by bit and we'll see how it goes. Yeah, this is what I was looking at last time. You see, it talks about the 4 states here. Like the write to PSG sequence, which would normally follow immediately after an address sequence, requires 4 principal microstates. Send NACT, inactive, put data on the bus, send DWS, write to PSG, and then send NACT. This last bit, I'm not actually doing that, I guess. Technically speaking, I suppose, like, what I should be doing is saying if I go to inactive and I just came from a read, or just came from a write, or just came from a latch address, then I should actually perform the thing, you know, that I'm supposed to do, rather than do it here. I could write it that way, actually. And I suppose what we're supposed to do is only allow values to be written or read or on all that. Let me see here. Everything goes through this DA, this data address bus here. Read from PSG, send inactive, send DTB, which will actually read from the PSG at that moment. Okay, so actually that's kind of right what we did. Read the data on the bus, and then we send inactive. Here it's the write. Put data on the bus, okay. Then we send the DWS to write to the PSG, and then we send it inactive. I think I'm going to keep what we have right now. It's good enough. Yeah, actually we need to keep it this way. I'm just looking at this. You go inactive and then you send DTB. So they mean we would go to the read mode here. And then after that you want to read on the bus. So we need to put on the data address on the bus itself, this value here. Yeah, so we're gonna leave it like this, so that when you do a read here, you're gonna get the value at the right moment. Okay, let's go zoom in a bit here. All right, operations. Since all functions of the PSG are controlled by the host processor via a series of register loads. A detailed description of the PSG operation could be best accomplished by relating each PSG function to the control of its corresponding register. The function of creating or programming a specific sound or sound effect logically follows the control sequence listed. Okay, so each of these sections talks about the different types of generators. We have the tone generator, the noise generator. We have 3 of these. R0 to R5 program tone periods, because that's what we control. We control periods. R6 is to control the noise period. We have mixer control. This is to turn on and off the different generators and how we want to mix them. So enable tone and or noise on selected channels. We have amplitude control, so that's for volume. Select fixed or envelope variable amplitudes. R10 to R12. And then R13 to R15 is the envelope generator control. So program the envelope period and select envelope pattern. Okay. Alright, that's very interesting. So I'm gonna need to model all of this, but we'll do this thing kind of one at a time. We'll focus on the tone generators first, and we'll ignore most other things and see if we actually can get something working. I mean, we're not that close actually. I still have a bit of work to do here. I also need to kind of hook up. There's still the part of implementing the PSG, and then there's the part of hooking it up to the VIA, which I still not 100% clear on, but I'm gonna be able to figure that out by looking at. I'm gonna do like how I usually do it. I'm gonna look at the BIOS routine, see how the BIOS interacts with the system, because I know that it does so through these VIA memory mapped registers. And I'm gonna kind of reverse engineer what it must want to do or how it's supposed to work from there, and hopefully we'll figure something out. Right now I'm gonna continue to focus a little bit on the modeling of the PSG. So let's look at the tone generator, because I think I'd like these 16 registers to actually. I have 16 registers here. I'd like to have some kind of enumerator that actually says what these mean. R0 to R5. Yeah, we're gonna have to look at this. So let's start with this. Tone generator control. So registers R1 to R5. What about R0? Fine tune register. Oh, so it should have said R0 here. Course. Yeah, this should have said R0. Lots of mistakes in these old documents. Frequency of each square wave generated by the 3 tone generators, one each for channels A, B, and C, is obtained in the PSG by first counting down the input clock by 16, then by further counting down the result by the programmed 12-bit tone period value. Right. Each 12-bit value is obtained in the PSG by combining the contents of the relative coarse and fine-tune registers as illustrated in the following. Let me see here. Okay, so basically what it's saying is we use 2 8-bit values, right? But we only care about 12 of those bits. That's what this means here. We don't care about the top 4 here. They call fine tune. Okay, so they call the low bits the fine tune, and I guess that makes sense. And then they call the upper bits here, which are in the second register. So R0 would, let's say for example for A, R0 is what they call the fine tune. And for channel A, R1, these 4 bits here are the coarse tune register. Makes sense. And this makes a tone generator. Note that the 12-bit value programmed in the combined coarse and fine-tune registers is a period value. The higher the value in the registers, the lower the resultant tone frequency. Note also that due to the design technique used in the tone period countdown, the lowest period value is 1. Divide by 1. And the highest period value is 4095. Oh, okay, I see. So I think what they're saying here, and I think I read this somewhere else, is that even if you put zeros, it will still use 1. So yeah, we'll just have to make sure to guard it so that there's never a divide by 0. That's basically what they're saying. Okay. Yeah, I'm gonna start modeling this. I don't know if I'm gonna keep it, but we'll start this way. I'm gonna kind of do like what I did in my Vi implementation here. How did I do this again? Yeah, I did like this namespace register, and then I kind of did that. I think I'll do something similar to this. I don't know. I don't know if I'm going to keep this. But for now, it's going to kind of help me just... maybe I'll do like low, high. I don't really care about fine and coarse. Height. Okay. And maybe we'll write a little helper function here, and we'll say it's okay. Should I? What do I want to do? Channel period, I guess, and we can give it the channel number. Yeah, see, it's kind of weird here. I'd want to give it ABC. Maybe we'll do another. And actually, now I think about it, we're probably going to want this function to be a private member here. Okay. Actually, I'm just going to do this. So it'll be actually, it was just a low bits, wasn't it? Yeah. Oh, it's because it doesn't know what channel is. Okay, so something like this. Basically, we give it a channel, and then what we do is we get the index into our registers. So it's either going to be 0, 2, or 4, and then basically we look it up. We read all the bits from the first one. Oh yeah, and we have to make sure that it's never 0, right? So the minimum value will be, or it should be, the max of this and 1. Let's do this in another stage here. So we'll say in fact, I'll say period, and then we'll return period. And I'll just put a little note here. Hardware ensures period is never 0 in 1 to, what was it again? 65,535. Was it? No, it wasn't, right? It was 4,096 or 4,095. Okay, so that should get us to channel period. The equation is describing the relationship between the desired output tone frequency and the input clock frequency and tone period. Okay, so this is just about the frequency. So the frequency of the clock divided by, oh yes, and that's right, they were saying that you have to wait 16 clocks. Why did they do multiply here? Desired tone frequency, F clock, input clock frequency, TP10, the decimal equivalent of the tone period, So bits TP0 to TP11. So where TP10 is 256 CT10, decimal equivalent to coarse tune registers. All right, plus the decimal equivalent of the fine tune registers, sure. But I don't understand this 16 here. Oh, okay, because by weighting 16, clocks, that's basically, does that make sense? I would have thought this was 16 plus TP10. Because we count down the input clock by 16, and then further by counting down the result by the program 12-bit tone period value. So this is basically the time that the square wave is high, right? Is that correct? Okay, let me see here. I'll make some sense of this. Yeah, I'm just trying to remember. Oh yeah. The ratio of the high period to the total period is called the duty cycle. A true square wave has 50% duty cycle, equal high and low periods. So that's what we're trying to model here. Okay, and so what they're saying is, what's this? Wonky with my chair. Okay, there we go. All right, let's see here. So And let me pull up my NES emulator because it's been too long since I've looked at this kind of code. Just want to refresh my brain. Yeah, it was in here. Divider outputs a clock periodically. Note that the term period in this code really means period reload value. But the actual output clock period is p+1. Oh yeah. Okay. That sounds familiar. Duty cycles. It's all about the duty cycles. And then what are we doing here? We have duty and step. So, okay, so if it was 12.5%, it would be 0, 1, 0, 0, 0, 0, 0. Right. Okay, so this is more generic pulse wave generator. It's not really a square wave generator. But for us, we really want a square wave. Okay. So then here, when we're talking about frequency, we're talking about when we're talking about period, what I'm trying to understand here is, like, how long do we want it? Like, do we take this period and we make sure that half that time we're high and half the time we're low? Is that what we're supposed to do? Okay, I think I get it. This value that we count down, that's how long it stays low, then how long it goes high, I think. Does that make sense? Still don't understand this multiplication here. Let's see if this makes sense. If TP10 were 4096, yeah, it would be multiplied by 16. To a high of f clock over 16. So that, oh really? So it could be 0 then. That implies that TP10 could be 0. That doesn't really match up with what I read though. Okay. I don't understand how this correlates with what I'm seeing. It's saying that we have to always wait 16 first. First by counting down the input clock by 16. First counting down the input clock by 16, then by further counting down the result by the programmed value. It's saying that due to the design technique used in the tone period countdown, the lowest period value is 1. Isn't the lowest period value 16? That's what it's showing here anyway. Anyway, okay. It's okay. And this is very similar. Okay. So let's see. It would be something like if we were to write our square wave generator class. Hey, Mac Addict. First time viewing, but you've watched most of my previous streams on YouTube. Oh, that's cool. Hey, well, thanks for joining live. It's nice to have you here. I think I've seen your name before, haven't I? Mac Addict. Did you did you post on some of my YouTube videos? Or maybe I saw you on Facebook or something? Seems familiar. What did I do again here? I kind of liked how I had it here. A way to clock and then get a value. Yeah, I think that's what we're going to do. Here I was doing size t's. I wonder if that's... maybe. Oh, that's awesome. Writing a Game Boy emulator in C++, that's really cool, man. That's a fun challenge. One of my good friends, sometimes he's on here, he actually wrote a Game Boy emulator in C++ as well. And it was a cool experience. The Game Boy CPU is actually quite challenging to emulate. It's got really a lot of instructions, like a lot of variations on instructions. More complicated than the 6502, and I think even more complicated than the CPU for the Vectrex, which is the 6809. Oh, hey man, feel free to take the code or inspire yourself. Thanks. Yeah, I'm pretty happy with my debugger design. The code is not perfect. I think I have way too much code in here. At 1,200 lines. And a lot of this really, because I'm kind of stuffing everything in this CPP file at the top in this anonymous namespace. And I keep meaning to like move this stuff properly into the class and break them down into member functions, but there's like a part of me that doesn't mind the kind of functional approach I took here. It definitely meant that my code was more straightforward, and it also meant I had faster compile time, so that was kind of the reason why I did it this way. But now when I look at it, I'm like, damn, it's a lot of code in one place. But overall, I'm very happy with the kind of simplicity to the debugger. All right, so let's go like this, or just do value. So when we clock, and I need a current value, I suppose, or oh, I could just use period. Oh, and I need a reset value. Yeah, I'm wondering about these types here. I'll just size T. In fact, you know what, I'll stick to this. I'm just hoping mine will run on something lower power than my dual Xeon. Don't worry too much about that, really. Like, my opinion on that is, you know, our computers today are pretty powerful. Even a cheap computer today is really quite powerful compared to the machines of old. And, you know, like, obviously don't, purposely make your code pessimistic, but if you're writing in C++, and chances are you're going to get pretty decent performance out of it, unless you just, make some silly mistakes, but a profiler will catch that. My emulator for Vectrexy isn't actually the fastest. It's my laptop, which isn't that old, struggles sometimes to keep it at 60, and I know why. I've profiled it and I've seen where the certain bottlenecks are. A big part of it is the debugger, actually, because I have things where I can put watch points on any address, and these things cost time, actually. But it's fine. It pretty much runs at 60, and that's good enough. And if I really, really want to optimize it at some point, what I'm hoping to do at some point is split out the core of my emulator and have like a build with the debugger and like a build without, and then the one without the debugger would just be much faster. But again, like, don't waste too much time worrying about that. Try to just get something that works and worry about optimizing it later. Obviously, don't prematurely pessimize your code, but I doubt that if you're writing in C++, you're gonna go down that route. You're probably writing pretty optimal code as it is, even without thinking too much about it. Anyway, that's my feeling. Alright, so that's one thing. By making this unsigned, we have to do that thing. Then again, it's not really possible to get... I'm gonna put a little... I'm gonna keep this a bit simpler. We know that for the Vectrex, we're not gonna get a 0 period because it says that we have to wait at least 16 clocks. So we're gonna be setting at least 16. So we can actually keep this pretty simple. And it's for square wave, so we're gonna go low high. Or maybe we'll just do this. We'll say value there we go. And m period will be equal to the reset value. So something like this. Oh yes. What did I do again in my emulator here? Now I remember why these here were not in the anonymous namespace. Oh yes, and this is why Inline classes are annoying. I'm planning on taking opcodes as indexes to an array of function pointers in my CPU object and hoping the compiler optimizes it into a nice jump table. I think that would work. I think I've seen or heard other emulators do something like that. Yeah, that would make sense. Yeah, that should work. See, this bothered me. Whatever. Okay, let's move on. If I'm using unique pointer, do I need to do anything here? I might need to put the Yeah, I think I cannot rely on default constructor and default destructor for PSG because I'm using unique pointer here. See, I wish I could do this. What the hell? Oh. Oh, it's because I put int here. Unless I just use like that, and then I will have to cast this. I guess technically this can be an int. Okay. Okay, GCC supposedly does the same with switch statements, but I'm using Visual Studio, so I don't know. I use Visual Studio for mine, and I'm pretty sure, yeah, that's what it does. At least when I looked at my NES emulator. Didn't really take the time to look here, but again, it runs quite fast, my CPU, so I think it does use a jump table. We could always check. Let's see. Because I'm definitely doing a big switch case. Like, this is my big switch case, and I end up calling a bunch of functions here, right? Let's see if we can tell it if it's a jump table. Just give me a second. So let's see, we do a test here on the opcode, then we have this, what do we have here? In fact, what we have here is probably even more optimal, right? See, that's a lot of the code gets inlined here. Oh no, this does look like a jump table. Yeah, this does look like, yeah, this is a jump table. See there, we're jumping here. And there's my opst. And then here we have a call to an actual function. Does this look like a jump table to you? Whoops. Sorry. I don't know if I can zoom in a bit. Sub jump. Compare jump if not equal. Yeah, like a lot of the code got inlined here because my function calls are actually templates, and they're all inlined above. So I think a lot of it just gets expanded in line here. So I don't know if that's... I guess it's not necessarily a jump table then, right? Because a jump table would literally mean just a series of addresses and then we jump and jump. It would be always like an extra indirection, which is effectively what you're hoping to achieve, right? Or no, what you're hoping to achieve is that you have this array of pointers and the code should basically, you know, dereference the table, get the location to jump to and jump there. But I don't know if that's always more optimal. I feel like, you know, here I kind of take advantage of the fact that with templates and just inlining, I get the code expanded in line for most of the cases. See, like this is op test. And this code for op test is completely expanded inline here. So, I mean, maybe this is a jump table because we are always jumping to the implementation, and then it's been expanded here. So I suppose that is a jump table. Some of these have not been optimized, like these read calls, but that's fine because these are these would not be inlined. And then we jump back here. Here's another jump here, and now we've jumped there. Yeah, so that's a jump table, right? Because we can see that it's always loading up where to go into RAX here. So it's using this dword pointer. This is the jump table that it built. R8 would be... Oh, what is that? That's the address, I suppose. R8 got image base. EAX into ECX. R8 plus RAX plus 4 times this. Yeah, this looks like it's getting the address of the jump table, and then it jumps to the value. RAX must be the offset of the pointer. Yeah, this is the pointer, this is the offset, and then we jump to it. So there you go. Visual Studio is building a jump table. So personally, I found it pretty simple to just do like a big switch case like this. And like I said, in my case, for my CPU, it made sense for me to make these templates because what I generalize here is the way we read memory, and the operation is always the same, but the way we read, like getting an effective address, always depends on the address mode of the specific operation we're doing. And so I have this compile time lookup CPU op here, which it did not go to. So here, see, compile time lookup. So it's kind of cool actually. It's a constexpr function that references these constexpr define tables, which I would like to show, but my Visual Studio has suddenly stopped responding. Yeah, that's what I'm going for, but CPU time is so cheap now, I don't know if it's entirely necessary. It's not like back in the day when most emulators were hand-assembled by really dedicated hackers. Yeah, exactly. I think you're talking about my earlier comment about like not spending too much time worrying about optimization. Wow, it's like... What the hell's going on? Visual Studio is completely not responding. Excuse me. Just give it another second here. Because I can see that on Task Manager, it's using CPU, so it's doing something in the background. And it's very rare that Visual Studio hangs this way, with no indication whatsoever of what's going on. Really odd. No disk I/O. What's going on here? But it's using CPU. So this one's okay. Come on, come back. Come back to me! Alright, I guess we're gonna kill it. Let's try that again. I mean, I don't know if you want me to show you this, but I'm pretty happy with the way this works. Speaking of optimizations, do you think it's necessary to declare CPU registers as static? You mean when you say making them static, you mean like a static variable so that they have one location in memory? Is that what you mean? Because I really don't think you need to worry about that kind of thing. Like, you effectively want to make them global, or have static storage. I don't think you need to do that. Okay, let's see if I can actually show this to you. Oh, this never works. F12 doesn't work on my lookup CPU. Okay, so this file, CPU opcodes. In here, I have this inline const expr. Oh look, it's doing it again. What the hell? What? I've hit some like nasty bug in Visual Studio when I try to look at this file, and this is new. This is terrible. Well, if I can't show you in there, I can at least show it to you in VS Code. Let's see. So yeah, so I have this struct here, which represents all the fields of my table. So I have the opcode, the name, the addressing mode here, the number of cycles it takes, the size of the op. Well, you know, you would think that maybe it's OBS, but actually my CPU is not even maxed out right now. No, it's really a bug. There's just literally a bug. It's specifically in that file. Like I click, oh, okay, did it? No, that's wrong Visual Studio. Yeah, no, it's really not responding. It's doing something. Like I'm gonna, you know what? Okay, let's try this. I always suspect when I see things like this, I suspect what's it called? IntelliSense. Sometimes the IntelliSense database gets corrupt and bad things happen. Although I haven't really seen a hang in a while, but maybe. So actually, before I open it, so you've really been watching my my YouTube videos. Have you actually been able to watch like most of them? I'm always like flattered when people actually take the time to listen to my videos. Some of them are just me reading and stuff. I try to make it interesting, but okay. So what I wanted to see here was would be in build. Yeah, let's just delete these files here. Let's see if we have better luck as it regenerates these IntelliSense database files. As soon as I hover over CPU page, ops page, you know what I think? I think this is, because it's all a const expert and it's all inline, it's probably running the IntelliSense on it, and it's just taking an enormous amount of time to get through it or something. Or maybe it's like stuck in some recursive loop. I don't know what's going on here. I did notice that there's an update for Visual Studio, so you know, I try to keep it up to date, and it's possible that they've introduced bugs and they fixed bugs now. So we're just not gonna go in that file for now. Hopefully, hopefully Visual Studio will be fixed. But I can still use VS Code at least. Oh, well, that's really cool, Mac Addict. I appreciate that. I'm assuming 81 means you're born in 81, which would only make you a couple years younger than me. Did you actually, if you are born in 81, did you actually play with a Vectrex? Were you exposed to one as a child? So yeah, so I have this big const expert inline table, and the inline here is kind of interesting, right? Because this is a feature of C++ 17 that says this is a global variable, but we don't need to have a CPP file for static storage. So it kind of gives us the best of both worlds. It allows us to have one instance of this that is shared across different compilation units, and because it's completely visible, it can be completely inlined. So it's really quite interesting. So I have this big thing here, and then I have this compile time lookups CPU op, where you give it a page and an opcode, and it actually goes at compile time and figures out, like if you gave it page 0, it looks in the CPU page 0, otherwise it recursively calls find CPU op because of reasons, and then eventually it returns a CPU op, which is a reference to that data structure up here. And in there, the most interesting bit is the addressing mode. If we go to CPU CPP, the addressing mode, what that does, I can just show you. Okay, so here we have these functions: read extended EA, which is effective address, and then I have read 16-bit effective address based on addressing mode. So here you pass it an addressing mode, and you can read, like basically you're never supposed to invoke this one, but if the addressing mode, where is it again? Okay, yeah, we declare these functions that are not, okay, let's focus on this one. I think that they're at the bottom. Yeah. So here are these 3 versions of that template functions, but that are specialized. One for when addressing mode is indexed, one for when it's extended, and one for when it's direct. And so at compile time, when we call read, like when we call this guy and we pass it the mode that we want from that table, it actually at compile time replaces it with this call. And that's pretty much the main difference. Like that's the only thing that really varies for me on this CPU is getting the value, you know, the read of the value based on whether it's an indexed, extended, or direct. So most of my code looks like the same. It always pretty much starts with, at some point I need to read the effective address and I do this compile time lookup. And then after that, the code is the same all around. And so then you see in my, if we come down here, you'll see things like this. Arithmetic shift right is called at different points. And each one of here, this is kind of sucks. I have to duplicate the opcode. And then I pass in here the different registers if I need to. And then that opcode is what's used to do the lookup at compile time. So all of this gets kind of munged at compile time into this expanded template code. And it gets all stamped out, and then the inliner, the optimizer, comes in and inlines most of the implementations in a jump table. So yeah, it's pretty sweet. I have to say I'm pretty happy with this implementation. I was born in '81, but I'd only ever heard of the Vectrex. Yeah, it's a pretty esoteric console, not super popular. But I was fortunate enough to have one. I loved it as a kid. I didn't spend like millions of hours of playing it. You know, I'd break it out every once in a while and I'd play, and I thought this was pretty cool. What I found interesting about the Vectrex is that how it ages. You know, as I got older, you know, I'm actually somebody who really played a lot of NES, and so I wrote a NES emulator because of that, and I really love the NES games. But you know, when I show people, like when we play old games with people, and people who didn't have the same exposure that I did, they look at those games and they find them really dated. You know, large pixels and all that. Of course, it's for me, it's all nostalgia, and I love it. But when I show, you know, say I show young people today, 20-year-olds, a Vectrex, you know, yeah, it's, you know, kind of basic and stuff, but the fact that it's vector based, then there's no big fat pixels everywhere, and it's kind of like these lines, and there's a kind of a natural decaying effect, so there's this kind of natural blurring that's going on, makes it really kind of cool. You know, it still looks really nice. I find that it ages well. So that's kind of something interesting about vector-based games in general. You know how like Geometry Wars was a big thing, I don't know, like 10 years ago? And who would have thought, right, that like a vector-based game like that would have been so popular? But yeah, I think it's because there's something about that aesthetic. It's just really pleasing, and it doesn't get old, you know? Alright, so let me get back to PSG. So where was I? Yeah, I was having this thought here. This is not going to work. And what's not going to work here is I want to be able to set the period on my square wave generator to be, we saw that we could put 4095, plus we're going to need 16 extra cycles. So I'm using UN16Ts, and I won't be able to store that in here. So I'm probably going to make these 32-bit just to like keep it simple. The value, whatever. I don't even know if I want the value to be 16. We'll see. Okay, so yeah, so here's where like we are doing a write into here, but really now what I'm gonna need to do is actually write to my square wave generators. You know what? Let me allocate that. Slowly but surely, we'll get there. I think it's init that I do everywhere. New square wave generator. Something like this. Yeah. Just thinking how I want to map this. Do I want to do this? I just watched Ben Heck do a Vectrex accessory teardown the other day for the 3D headset and was really impressed with the engineering design and how ahead of its time the Vectrex was in some ways. Oh man, absolutely. That 3D headset thing, it's crazy, right? Like how they synchronize the pinhole and like apparently it's not even the same. Like every game could decide what rate it wants to run at to synchronize. So there's this like communication channel between the headset and the game. And it basically synchronizes, like the game kind of clocks its own its own frequency for that spinning thing. So there's like a startup period where the headset's spinning wheel needs to be calibrated for the game, and then after that it starts. So yeah, it's really quite neat. I feel like when you go back to the 80s. You can really see a lot of experimentation in the games realm, and then it was like almost nothing for a long time. You know, like it kind of died down in the 90s. Like in the 80s, you know, Nintendo, they did. I mean, I guess even early 90s there, but they had their robot and they had all these peripherals that they were trying. They made their what's it called? There the Virtual Boy. So that was their foray into virtual reality. And then after that, you know, for a long time, consoles starting with, I'd say, you know, Super NES and up, N64, let's say N64, PS1, all the way up until just before we started doing VR, consoles were pretty much the same, right? Just this thing with a couple of controllers. I mean, the Wii, I guess, kind of did something a little bit different, but not so different. So yeah, I think it's really interesting to see the Vectrex in 1981-82. They were trying to come up with these virtual reality goggles, and they had like the light pen that you could draw on the screen, which was pretty neat. And just the idea of even just shipping a console with a built-in screen, and trying to come up with something that consumers could take home like that, you know? It's pretty out there as an idea. That's not set bits, right? What is it I want? I want... Didn't I write a write bits? Oh, anyway, I really don't need to do it this way. Let's do... Well, actually, it would be nice if I had set bits that did this. Why didn't I do that? This should not have been called set bits. It should have been like clear bits or something. Oh, I see. Yeah, I don't like this. Whatever. So what we want here is high, shifted left by 16, ORed with the current period. Love the Virtual Boy. I still play Red Alarm and a few others on an emulator on the TV with anaglyph 3D glasses. Oh wow, that's cool. I actually have never played with one, and the only emulator I've tried is Ferris's, the Rust Jewel Boy. Mostly because I'm just learning Rust, and I just thought it was amazing how easy it was to get that building. Oh, that's headaches. Yeah, no kidding. That's what I keep hearing. Do I need to really mask the bits off? Suppose not. Cool. I guess this is the same thing, or equals with that. Yeah, I think. Alright, so if I do it this way, I don't really get that extra 16 count, do I? But I could do it here. We can kind of build it into the square wave generator. 2 const expr. All right, but then I'm not calling set period here. So no, it's not here that I need to do it. It's in my reset. Plus 16, it's here, plus min period. And I guess I'm not really setting the period as much as I'm setting the value to reset to. So I guess what I want is the period and then the current period value. Maybe that would be a better name. Period counter or something like that. Yeah, let's do that. That will be a bit more sensible. So we set the period. This goes away. So like this. I need to write it better. I don't want to be doing this. Anyways, okay. Period high. We want basically top 16. It's not right. What I want is how about we just do this? In fact, we only really want 12 bits, right? So what's that? All right, FFF. Yeah, that wasn't even right. No, that's it. No, we want just, what am I saying? We just want 4 bits. This top nibble here. Yeah, maybe I should mask off bits. put some sanity checks here just to make sure that my code is right, and then we'll see, because maybe the data will come in, maybe there'll be bad data. It's possible it's because the ROMs could always set a larger than 12-bit value, in which case we might hit these asserts, but if we do, and I can see that it's coming from the ROM, then that's okay, it's not coming from my code, and we'll just mask off the bits that we don't want. And then we should be okay. Put some notes here. Period, it's going to be a 12-bit value. In fact, we'll use my checked static cast just to be sure. So that's the target, and we just pass in the value. Yeah. Of course, I do all this and I never run in debug, so I don't think any of this will matter, but we'll run it in debug at least once, make sure. Trying to understand. Oh, it's because of the line length. Okay, so we've got a square wave generator. Now I need to figure out what I want to do here. Because basically, when we read or write, I'm currently just using this register thing, but that's what we want to replace. So see, the latched address will be this here, and we're going to want to map it. See, it'll be something like this. When it's channel A high, then we want to store into the bus. Maybe we want to do this in a function, I guess. We'll see. Yeah, let's do this in a function. Create a definition. Okay, we create those functions. Did I put that at the right place? Yeah, I did. Alright. Then basically what we'll do here, this is going to be replaced with m_da equals to read, and we'll give the latched address. See, the reason why, not only will this be a bit cleaner, but it allows us to do early outs, which I much prefer. Right at the latched address, the value on the bus. Now here, we're just gonna do period high like that. Oh, and yeah, this will not return a 16-bit value. Yeah, I am not thinking straight. These are 8-bit values. Of course. And there's no need to assert this, obviously. We will assert this. Okay. Slowly but surely. So we return here like that. Channel A low. Be very similar, except period low. I mean, it's a bit repetitive, but you know what? I don't mind. Sometimes a little bit of repetition and the code is very clear. And we have a very limited number of cases here, so nice for debugging. Not everything has to be, you know, generalized. And otherwise, for now, we'll just return whatever value we put in this array. Does that array have a, I always forget, a zero initialize? It has fill, that's right. I think I am going to do the fill, just to be really sure that it's clean, full of zeros, because we are not doing that here. Oh, I have a reset. Oh yes, reset. Oh, hey, Meshu. How's it going? And the number of viewers has risen. It happens sometimes. I did do one thing differently. I decided to start actually changing the name of my stream and to try to put what I'm planning on working on rather than just putting always the same generic title. So today I wrote episode 82, Vectrexy, Implementing Sound. So maybe that attracted some people, I don't know. Yeah, I'm all right. I was sick last week, as I tweeted. That's why I wasn't streaming last week. Just had a cold, you know, but one of those gross ones where you're like hacking all the time and feel like crap. But yeah, I'm good. I'm good now. Okay. So, and then similarly, we're going to want to do the same kind of thing in write. do it on time here. Wow, it's already almost 11. Holy crap. That went fast. I think I forgot to tweet that I was streaming. Oops. Oh well. Anyway. So Meshu, you're asking, am I using shaders? I am indeed using shaders. Mac Addict, clarity is way more important than creating terse code, especially when you're posting the code publicly on GitHub for programmers of various skill levels to peruse. Yeah, that's a good point. Although I have to say that's not really a driving force for me. Because I mean, I do think some of my code might be difficult to grok. I do think the CPU code that I was showing earlier isn't the easiest code to understand with all the template stuff. But I kind of write it just for myself, you know. It's interesting how, like, you know, when you start programming and you, like, you know, you copy paste a lot and you don't really generalize much because you're not used to that concept. And then later on, as you learn more and you learn about generalizations and don't repeat yourself and all that, well, anyway, I went like completely extreme and like was like never repeat, you know. It's like as soon as you copy paste twice, it's time to refactor it. So you do that for a while, and then you kind of realize, no, you know, there's kind of this in between, right, where you want to balance the ease of being able to debug it and write the code and understand it, but also, you know, not go crazy with the too many layers of indirection. And it's really kind of a difficult balance to. It's hard to like describe, you know, what exactly that means. You know, there are certain rules out there that people like, you know, rule of 3 or whatever. If you've done it the third time, it's time to generalize or something. But it's not always the case, you know. It's kind of an art, right? Figuring out what that balance is. And I'm not saying I've mastered it or anything. I still, you know, write code that I'm like, what did I do here? But, you know, definitely, I think my code's more straightforward than it used to be for a while. I just try to kind of write it straight up the way I think, you know, the most simple possible way. And then later on, if I feel like it's getting painful, that I think it's more that it's kind of, if I feel the pain point, then I'll refactor. But I don't do it too early in case of a pain point, if that makes sense. Oh, hey, Raptor. I think Raptor agrees with me. Yeah, actually, I was mentioning you earlier, Raptor, because Mac Addict is working on a Game Boy emulator in C++. And I said that I know someone, one of my close friends, which is you, who did the same thing. So yeah, if Mac Addict, if you want to see an interesting Game Boy emulator implementation, Raptor could share a URL with you. Oh, this is garbage what I did here. I guess I don't really need to mask it here. You can mask it on the way in, rather. Yeah, and take this off. It's just noise. Period low is just a... Yeah, this technically is a read bits. Oh, I think it's read bits with shift that I wanted, because maybe we could go back technically to what I had here. Oh yeah, the Blarg suite. I used Blarg's test ROMs for the NES emulator as well. That guy's a legend. Yeah, so what I need to do is write bits with shift so that I can stop doing this kind of crazy crap here. I don't know if I should write it this way instead. That more clear? Not really. At one point you start thinking it's actually more clear when you don't use these functions. Let's just do this. Okay. Okay, so now what I want to be able to do is I'm gonna have to use there's channels that tell me whether or not these channels are there's a register that controls whether these are active or not. Now, being active just means whether we mix them, not whether we actually advance them, I suppose. So I suppose we should always advance the generators. So let's just do that. Okay, that's cool. So what's next is, so technically we have the ability to play music through the square wave generators. There's the bit about, like I just said, figuring out whether they're on or off and actually mixing those values. And then there's the part about resampling these values at the frequency that we need to hear this and actually put that into the sound buffer for the audio driver. There's also the part of plugging the PSG to the VIA so that we can actually get these values, which is probably the thing I'm going to do next. So Mac Addict is saying, I'm one of those weird people that makes a skeleton program and then exhaustively researches a subject before writing a single line of usable code. I don't know if that makes you weird. I think that's how a lot of people work. I'm certain, you know, surely I've done that too. I know when I wrote my NES emulator, I read a ton of stuff before I even got started. And for Vectrexy, it was a little bit less because the NES emulator was my first one. And I think when it's your first emulator, you just want to kind of wrap your head around the tech and understand what you're dealing with. And for me, I had never really written an emulator, and my goal was not to look at code. So yeah, I had to kind of like think about how I was going to do it all. And you don't want too many false starts, so I can understand that. So, even though it doesn't do much right now, it does run. We don't hear anything, that's okay. We're gonna get there, but we're not crashing, so that's a good start. And I think this is a good point to commit what I've got. So let's do that. Oh, actually, I just realized most of the coders I know personally are the dive in and fucks all the time. Well, right. I think the last part of your sentence there is why you want to avoid that in general, right? I mean, sometimes that's the strategy, right? You just want to kind of explore and just try something. It's funny because definitely since I started using Git, I find myself doing that a lot more. Just, you know, experimenting and throwing in a bunch of hacked code in a CPP file and seeing if it works, proof of concept type of thing. But yeah, in general, you want to have a bit of planning in there. Yeah, Git's great. You know, I know the CLI is nasty and a lot of people have complaints about stuff like that, but the fact that you can create branches so quickly, it's just amazing. Yeah, so I was going to say that I think this function here is going to be completely useless to me now that we've pushed that implementation into the square wave generator. So yeah, this here is not useful. Let's do that there. Oh, maybe I'll move it here. Yeah, because this might actually turn into, because there's actually another channel which is the noise. So this should probably be like square channels or something. Maybe not, because we can assign the noise to the channel. Yeah, okay, so I'll leave this like this. Yeah, this makes sense. All right, getting tired. I'm gonna be wrapping this up soon. So what do we do? Start implementation of square wave generators. What else? I guess that's pretty much it. GitHawk, eh? Never heard of that one. Guess that does a good job of allowing you to scroll through code and stuff like that. I will push this. I realize actually I haven't pushed in a little while, so let's do that. Speaking of being able to peruse code. Alright, well guys, I think I am going to call it a night. I am still a little bit tired and need to rest. So thank you so much for watching. And guys in chat, Mac Addict, Raptor, Meshu, thanks for hanging out. And yeah, I should be back in a couple nights. So yeah, thanks again.